Boom. We're good. Hey, so guys, the reason that we're doing this is twofold. And I think the way to talk about this is by looking at this organizer as a place to start. So guys, when we launched into the content that we're covering in the next couple days, we talked about the idea that our driving purpose here is to figure out where the numbers come from those thermochemical equations. So if we know that a reaction releases some amount of energy, how do we know? And guys, we're part of the way there because we said there's two ways to do it. Empirically, that's lab, and then through a lens called Hess's law. And so guys, yesterday for an hour and 45 minutes, we did calorimetry. We did it in second period superficially. We did a super deep dive into this third period when we started talking about accounting for where all the energy actually goes. And then guys, I had several of you come and talk with me. Dallin swung by and he's like, I think I get the concepts, but the math is a little mushy. And guys, you've got to understand that when you all say things like that to me, I don't take it lightly. Dallin is super bright. And so when Dallin comes to me and goes, this is not clicking, the first thing I think is, why? But then I also think if Dallin's not understanding this, probably others are also not understanding this. Guys, that got reinforced yesterday when a couple of you threw on our group me, hey, I don't know how to do number 10. I think Ami started it, and Nora, you chimed in. Ami came in this morning. And guys, that even further reinforced this idea that we are not yet done climbing down the left-hand side of this dichotomous key. So guys, if you, and I'm not throwing you shade, if you can't do number 10, and I even heard Sharp talk about this earlier, I was eavesdropping on you, and he was like, I made that way harder than it needed to be, right? On number 10.
I did it, and I thought I had the right answer. And then I went back and tried to teach more after it. And then I realized that I actually did not.
So maybe you made it easier than it needed. Okay. Yeah. So guys, my initial intent was this. Let's talk about it third period because it's really lab. But guys, at the end of the day, it's not. This is second period stuff because question number 10, guys, grab your labs. Guys, question number 10 in the pre-lab is not the full banana. Guys, question number 10 on the pre-lab is not the way that we need to know this for the lab. Guys, this is the superficial, the way you need to know it for the lecture and the test and the AP test. And so guys, all of those things coming together tells me we should do this together right now. The other reason that we're doing it right now is because we have a lot to do third period. And so we're just going to do it now. So guys, I would encourage you to grab another sheet of paper. I would, if you need, and then you'll turn this in as a part of your pre-lab. But guys, we're going to do a deep dive on lots of things that you should understand. About number 10. You guys ready? Do you have it in front of you? I think I know the numbers. JD, you good? Okay. You guys good? So guys, you read a question like question number 10 and you're like, I'm not exactly sure what this is talking about. So it's the very first thing you do? Draw a beaker. Seriously. So you draw a beaker. And guys, now you can place the components of this system, this dissolving thing, in your beaker. So guys, in your beaker, you have 100 grams of water. And then initially, outside your beaker, is it 3¼ grams? Yeah. Guys, initially outside your beaker, you have 3.25 grams of NaOH. So guys, what is your system? The sodium hydroxide. What is your surroundings? Water. Guys, why is it not everything else? And if you're not sure, read that weird little skinny sentence down at the bottom. It says, assume the calorimeter is a perfect calorimeter. And guys, that is the way for them to say, don't worry about the energy that goes into the calorimeter. That now makes this a second period question and not a third period question. If it was a third period question, we would need a calibrated calorimeter that we can figure out the heat capacity of to know how much energy went into the calorimeter. Get it? So guys, this is a second period question. Please stop me if you need along the way. So then guys, what we're going to do is we are going to put our chunk of sodium hydroxide into our water. So now guys, a question. What direction does the energy flow? In or out of the system? How do you know it's out? How do you know it's out? What evidence do you have? The water is heating up. Guys, that's it. You're right, Nathaniel, that it's exothermic. But guys, the evidence that we have is temperature change. Remember, we can't directly measure energy. We measure the effects of energy. One of those things is temperature change. So guys, the temperature goes up. Please feed me the numbers. 23.9 to what? 32.0? Okay. So guys, here's the first thing that we need to talk about. In physics, you get very, very careful about organizing temperature changes so that the sign of the temperature change reflects whether things are going up or down. Guys, I would suggest to you this. Always make your temperature changes positive and then figure out the signs at the end of the problem. It makes things so much easier. So guys, in here, we are always going to make our temperature changes positive. And if I can do math, this is 8.1 degrees Celsius. All right. So now guys, here's what we know. We know that energy is going out of the system and into the water. What we want to know is how much energy goes into the water, because if we know that, we know how much energy came out of the system. So guys, in order to do that, we go Q is equal to MC delta T. Now guys, Q is the amount of energy. Well, I'm running too fast. It's important you hear this. So guys, Q is both the amount of energy that the system is losing and the amount of energy that the surroundings, the water, is gaining. Does that make sense? Says who? First law of thermo. Energy out is energy in and vice versa. Okay? All right. So now guys, we need our numbers. They will give you this on the AP test, but the specific heat of water is 4.18. We've already established our temperature change, 8.1 degrees Celsius. Guys, what we need is the mass. Is it 3.25? Is it 100? Or is it 103.25? It's actually not. It's also not 3.25. It's 100. So guys, let's talk about why. This is where system and surroundings becomes really important. So guys, the system is your 3.25 grams of sodium hydroxide. But this is describing the amount of energy gained by the water. Therefore, what we need, and forgive me for being loose with significant, does it really say 100.0? Oh, then we're fine. All right, well, we're fine. So guys, this is the mass of the water. Not the mass of the system, 3.25, not the mass of the sum. Guys, for this reasoning to make sense, the 3.25 grams of sodium hydroxide is our system. It's not where the energy is going, it's where it's coming from. And guys, we will account for that in just a minute. Please. So You're taking, but it's really the water. So in a calorimeter, in second period, in a calorimeter, the assumption is that the calorimeters are perfect. Therefore, energy is not going into the calorimeter. It's only going into the water. So when you do these calculations on the test or the AP test, the mass will always be the mass of the water. Is that what you were saying? Go ahead, Adam. Yeah.
Into the water before it's dissolved or as it's dissolving right now, is it going to absorb energy from the water because it's at a different temperature than the water? And we have to count
They should both be at the same temperature, room temperature. And actually, just a little foreshadow. You know that we're going to do the calorimetry lab that we're working on Tuesday. And then we're going to bounce back, and we're immediately going to do this lab. So in the lab that we're prepping right now, it's a heat of neutralization lab. What we're going to do next is we're going to do a heat of solution lab. And so at that point, the water and the salt, they're both at room temperature. And so, yeah, go ahead.
Sorry, so,
No?
So for the 4.18, what's the
Uh-huh.
specific
Of
water?
water. Good.
Yeah, so this is
Yep.
water.
Yep.
Do we need the units?
Yeah, so I mean, it's not wrong to go joules, grams, Celsius, degrees. And when you do, the grams cancel, the Celsius degrees cancel, and you're left with joules. So, but frankly, if you don't do it on the AP test, they'll let you go. Is that okay? Okay, so now guys, we do the math. Can someone help me? So let's call it 3,400 joules. Okay. Now guys, read the question carefully. This is not the answer. What does it say? What is the enthalpy for this process, the enthalpy change, delta H for this process in kilojoules per mole? Now we are going to account for the mass of the sodium hydroxide. Because guys, the question is this. We got 3,400 joules. But guys, how much sodium hydroxide generated 3,400 joules of energy? 3¼ grams.
But we also need to do it in
Correct. So what we need to do is we need to convert to kilojoules per mole. Because guys, those are the accepted units for enthalpy change. So now 1,000 joules is a kilojoule. And guys, please, if I solve this problem with you, I led you to a point of failure. I'm going to lead everybody to that point of failure. Please let everybody have the same experience you had when I worked you through this. Then guys, this is sodium hydroxide, 23, 16, and 1. 40 grams is 1 mole of NaOH. And we've got 3,400 divided by 3.25 divided by 1,000 times 40, and I get 42 kilojoules per mole. But guys, this answer is wrong. Thank you for letting everybody have this moment. This answer is wrong. You put this on the AP test, you get 0 credit for it. What's wrong? No. Good, Dell.
Is it the beginning part of 3,400 joules over 3?
No, the math is all fine. Go ahead.
It's not because it's also.
You could put moles of sodium hydroxide, but you would be fine if you didn't. Nora. Oh, sorry. No, go ahead.
That's not the apple.
Yeah, go ahead. It's negative. Guys, this number is negative. How do we know? Well, it goes back to the reasoning we engaged in before. Nathaniel said it was exothermic, but I didn't let him stop there. And then Dallin chimed in and said the reason we know it's exothermic is the temperature is going up. But now, guys, hear this carefully. If the temperature's going up, doesn't that mean energy's going in and that should be positive?
No.
Yes. But what's wrong with that reasoning? That's going into the water, and this is the enthalpy change for the system and not the surroundings. So a rise in temperature of the water indicates a negative enthalpy change for the reaction because it's losing energy into the water, causing the energy's temp to go up. Does all of that come together in your brain? Because this is why I really wanted to do this, because now is the time to have this conversation. So it's negative 42 kilojoules per mole. And whoever said it, you're not wrong. You could put mole of sodium hydroxide here. The reason that you don't need to is because if you look at the lab, you'll notice the balanced equation is given, just the dissociation of sodium hydroxide. And what you've done is you found the delta H for that reaction, which is balanced with 1 mole of sodium hydroxide. What do y'all think? Go ahead.
This is a little bit on the topic, so we can stop being so much.
Stop. No, I'm just kidding. Go ahead.
So I know we're being like super careful about significant digits or whatever,
Mhm.
but when I was doing it on my own, I ran into this problem. So 34,000 joules is 2 significant digits, yeah?
Yeah, 3,400, but yes. Yeah, you're fine.
Is 2 significant digits.
Yep.
And, I think the most amount of significant digits we have in our calculation is 3 significant digits. 2.
Yeah, good, Dallin. Yeah, so remember that when we subtract, it's not significant digits, it's decimal places. And that, good for you, that's the 8.1, which then limits at the end.
Right, I didn't write it down.
Yep.
One, I wrote 32.0 minus 23.9 in parentheses.
And then you just ran with it, yeah.
Just out of curiosity, though, because I forgot from last year, if you do, the number I got was like, you round to 3,400 and
Yeah.
all the way down to like
Yeah. Yeah.
2 decimal places.
Right.
How do you make that to 3 significant digits?
Make what?
How do you round it to 3 significant digits? So if it was like 39.89.999.
Yeah, in theory, you'd have to put it in scientific notation.
Right.
Yeah, but here, guys, let's just talk about it now. This is weird. 6 years ago, I think, they wrote significant digits out of the AP Chem test. They said students can use as many as they want. Just write them down. And chemistry teachers around the world were screaming and kicking because we're like, now the kids don't have to know significant digits. And then the next year they took it back. And so the rule now, and this is the rule for the test you'll take, you have to be within 1 significant digit of the actual answer to the question. So you can have 1 extra or 1 too few significant digits, and then your answer could be wrong by those digits, and you'll still get credit for it. So, all right, you guys good? Okay, so guys, this then provides the transition into what we're doing now. So putting on our second period hats and joining me here, guys, this is where we're going to pick up.
I think we should get back to the second. So every time we trade here, we make it just
Yeah, we did that 2 years ago.
we should get like a visual impact.
No, they were IKEA bucket hats. There you go. I like it. Okay. So guys, you know, I think you know this about me. One of the things that I love about teaching is that I actually learn while I teach. A lot of times I come into class with a loose idea of what we're going to do. And really, it's one of the things I love about teaching is I'm doing a lot less telling and a lot more of guiding conversations. I don't know if you've picked up on that, but it's one of the things I love about teaching. And guys, that led me to a really interesting realization 3 years ago. So guys, what we're going to do today is we are going to cruise down the right-hand side of this organizational chart. So remember, the big idea is, where do we get numbers like 42 kilojoules per mole for the dissociation of sodium hydroxide? And we just found out that we can do that empirically. We can do it in a calorimeter. We can gather the energy, put it into water, change the temperature of the water. Doing a little simple math, we can come up with delta H. Yes? But guys, it turns out that there's another way to do this, and it doesn't have to happen empirically. You can actually do this through something called Hess's law. And guys, when you see Hess's law on the test, you're going to see there's two ways to do this. One is computational, and the other one is through a process of manipulation. Now guys, here's what's going to happen today. I'm going to explain to you Hess's law. Then we are going to do Hess's law through manipulation. And I'll tell you, this is what to look for if they want you to do manipulation. But then guys, we're going to solve immediately another problem doing it computationally. And you're going to find out they are exactly the same processes, so long as you understand the chemistry. And it's actually really cool. So guys, to be ready for this, you need a calculator. You need your books. Open to chapter 5. And you need the class notes that you started previously. You guys all set? All right. So guys, please do not write any of this down, but if you understand what I'm about to explain to you, you understand Hess's law. You ready? To understand Hess's law, again, you're not writing this down. This is I-15. Again, you're not writing this down. And guys, I think that most of you know that my Sunday, well, actually pretty much every day of the week, my relationship with my church is a lot different than probably a lot of yours. You live within walking distance of where you meet for the most part. And so, guys, you have a really easy commute to church. It's actually one of the things that makes our church challenging, in that we have people that attend our church from Draper all the way down to Santa Quin. We draw from a big space. So, guys, I was thinking about Hess's law a couple of years ago, and it brought to mind a friend of my daughter's named Haley. So, guys, here's the deal. Haley lives in Lehigh, but one of Haley's best friends, and you got to understand, Haley's kind of a free spirit. One of Haley's best friends lives down in Springville. Not Springville, it's Springville. You know that, right? Okay. So she lives down in Springville. We live in Linden, and then our church is down in Orem. So, guys, let's see. So, Linden to Lehigh is about 10 miles. Linden to where our church is about 8. And then Orem down to Springville, where she lives, is about 20. So, this was Haley's Sunday morning. Haley would get up in the morning, stop at Starbucks, get all loaded up on caffeine, and she would drive all the way down to Springville to pick up Callista. Then she would drive back up to Linden to pick up my daughter, and then she would drive to church. So guys, I have two questions for you. How far was Haley driving every morning?
Distance or displacement?
When she gets out of her car, how many miles have ticked off on her odometer?
6 miles?
No, on her odometer. So this drive is what, 38 miles? And then, okay, help me. So, and then she drove another 28 back up to Linden and then 8 to church. Is that 74?
Yes.
Okay, so she drove 74 miles. But how far did she move?
18.
That's not the most true.
No, how far did she actually end up moving?
18.
Well, she really only moved 18 miles because she moved from Lehigh to Orem, right? So at the end of the day, that's the distance that she traveled. It's just she's going in all sorts of wacky directions.
If she stopped in Linden first, that would have been a spiritual practice or
Yeah.
shave off like a good.
Oh, but you got to realize this is Haley. She drives a Subaru. She loves her car. She loves to drive. It's just her thing. So now, guys, the question is this. What could we do to make these numbers simply add up to the overall distance that she traveled? Well, guys, now we need to give them signs. So let's say that the changes that she's making that are moving away from her house, we'll call those positive. That was good driving. Then we'll call the backwards driving, that's stupid driving, right? Okay, so is the 10 positive or negative? Yeah, she's headed down, right? What about the 8? Yeah, she's still doing okay. Down to here. But guys, what part of this trip did she not need to make?
28.
The 28 back, right? So this portion of this trip, which is really 28, is driving she didn't need to do. She's headed in the wrong direction. Do you understand what we're saying? So guys, if we give these distances signs away and back, positive and negative, if we can add up those numbers, it tells us the overall distance that she actually traveled. Does that make sense? Do you get the idea? Guys, this is what is called Hess's, I'm at the wrong chart. Just a second. I redid this down here. Here we go. So guys, this is what is called Hess's law. And it says this: if you have a reaction, and if you can break it down into steps, like driving from Orem to Springville to whatever, and if you can take this process and break it down into steps, and if you know the energy changes of the steps, kind of like knowing the distance of the shorter segments, guys, adding up those steps will give you the energy of the overall process. Let me get everybody here, and then I'd love to, Liam. Well, and actually, you know what? You don't even need to write this down. Guys, there's 2 ways to do this. Through manipulation and through computation. And guys, you don't need to write those down because they're going to be the headings of our next couple things. Liam, go ahead.
It's like a quick question, but like for, you know how like therefore has like 3 dots?
Yeah.
Is there something like that for if then?
I'm sure there is, but if then is really a conditional statement like therefore, right? So I think you could just use the 3 dots. If this is true, then this is true. If this is true, therefore this is true. Yeah. You guys good? Okay. So guys, let me cast the big picture for you. Could I? Don't write this down. But what are we really talking about? Let me show you. Again, don't write this down. So say that you've got methane and oxygen, and that's producing carbon dioxide and water. And guys, I believe that we alluded to this earlier. Thinking about the energy of this reaction, how does the reaction work? So what has to happen to the reactants for the reaction to take place? They need energy to break apart. So guys, this is going to break apart into carbon and 4 hydrogens. What has to happen to the oxygen? It has to break apart.
Probably a little bit more energy too, since it's double bond.
Interestingly, it's less. We'll talk in a minute. Yeah, we're gonna look at data. So guys, now they've all broken apart. then they're going to come together and they are going to form, being sloppy with unbonded electrons, they're going to form carbon dioxide in water. Now this, guys, looking at the reactants, does energy go in or out? As this reaction happens to take these molecules and break them apart, does energy go in or out? It goes in. So this would be endothermic and therefore a positive delta H. Now guys, what about on this side? Is energy going in or out? It's coming out. This is exothermic and therefore a negative delta H. So how do we apply Hess's law to this? Well guys, if we know the amount of energy that's going in, that would be positive. And if we know the amount of energy that's going out, that would be negative. You add them up and guess what you get?
Negative number.
The negative, in this case, yes. But how do you know that?
Because it's methane.
Yeah, it's hot, right? So we know that the number is going to be negative, but adding these two numbers together, the value that we get will be negative, but it will also be the amount of energy that's given off. Do you understand better now Hess's law? Positive is going in. That's kind of like driving south. Negative is going out. That's like driving north. And if you can add up your souths and your norths, if you can add up your positives and negatives, you get the overall energy of the reaction, just like you get the overall distance of the trip. You get the idea? Okay. So then, guys, the question becomes, what does this addition process look like? And guys, again, it can happen one of two ways. Please write down the word manipulation. So guys, this is what this is going to look like on the test. I would encourage you to write it down. It says calculate the enthalpy of combustion as carbon, graphite, pencil guts, turns into carbon monoxide. So you take your pencil guts and you light them on fire, and it reacts with the oxygen in the air, and it turns into carbon monoxide.
Not like carbon monoxide is like super poisonous.
Oh yeah. So guys, what we need to do then is we need to balance this equation. I'm going to switch to blue. Maybe. So guys, we need to balance this equation. And this is going to be a little weird. Check this out. So carbon plus oxygen yields carbon monoxide. Yeah, you saw this in the book. So guys, please do not write down what I'm about to write down. And actually, I'm going to move this over. You're okay. I'm not. So, guys, we've got carbon reacting with oxygen to form carbon monoxide. And what we're shooting for is the delta H for this reaction. So guys, now let's balance it. Don't do this with me. So now let's balance this. 1 carbon, 2 oxygens, 1 oxygen. So we put a 2 and we put a 2. But guys, this is wrong. Here's why. If you read the question, it says calculate the enthalpy of the combustion of how much carbon? 1 mole. But when we balanced the equation, we balanced it with 2 moles, and that doesn't get us to the answer that we want. Yes. So this is how we balance the equation. Well, wait until you start balancing equations with fractions like 5/9. And who said why? Why? And the reason why, it's a brilliant question. The reason why is because we're trying to get the enthalpy of the combustion of one carbon. That means our reaction, 1 mole of carbon, it means our reaction has to balance with the 1 in front of the carbon. And the only way to do that is by putting a half in front of the oxygen. You guys okay? Okay. Now guys, this is where you need to start becoming familiar with the way this question will present itself on the AP test. And guys, it's going to look like this. I really want you to take the time to write this down. But guys, do this please. Make it big. Make it like even as, so skip down, I don't know, a couple lines, and then make it as wide as your paper even. But guys, it's going to be important that you have like 2 or 3 lines beneath this as well. Sorry guys, this might freak out. Oh, it didn't. I'm waiting. I'm waiting. I know that's not what you're saying. Good, good. We'll talk. That's exactly the point. Ugh. You guys okay? Hurry. More power. Do you actually like these? No. It's barely food. Like my wife tried to trick me into eating those. I know. Doesn't help. They still taste like peas. Yeah.
Those are so good. Some specific flavors.
And carrots.
The carrot ones aren't great.
I've yet to find one that I can actually swallow.
They have apple cinnamon ones.
I would be okay with that.
Veggie straws, like S tier.
All right, guys. That was my effort to buy enough time for Ami to finish writing. Are you good? That a girl. All right, so, guys, Dallin brings up a really good question. He's like, wait a minute. That top reaction is carbon reacting with oxygen. And it's 1 carbon. But you'll notice, guys, that it's combusting to carbon dioxide. If it was combusting to carbon monoxide, we'd already have the answer. But it's not. So, guys, let me explain to you the way to play this game. On the AP test, when you see this question, here's what you're going to see. Sometimes this is called the subject reaction. Sometimes they will give you the subject reaction. Sometimes they'll just ask you to come up with it by giving you a little word thing like calculate carbon to carbon monoxide. But then, guys, they will give you other equations. Your job is to manipulate these equations. And guys, here's the way to do it. Follow along. You go to your subject equation and you say, okay, my first substance is carbon. Then you go down to your other reactions and you ask yourself 2 questions. Where is it and how much do I got? So guys, when you find carbon, the only place that you find carbon is right here. So, this is on the left and this is on the left. That's a win. Now, how much? 1 carbon, we're good. So guys, that means that this equation right now does not need manipulation because we looked for carbon, we found carbon, it's on the correct side and the correct amount. Now guys, this, skip oxygen. If you start trying to muck with oxygens, you're just going to dig yourself a pit. So now guys, this, carbon monoxide, same questions. Where is it And how much do I have? So guys, when you look, you'll notice that you find the carbon monoxide over here. Do we have the right amount? We do. We've got 1 and we've got 1. But what's the problem? It's on the wrong side. Here, carbon monoxide is a reactant, but in our subject reaction, it is a product. So here's what you do. You rewrite the equation. CO2 yields CO and 1/2 O2. Do you see what I did? I flipped that reaction over so that the CO is now a product. Guys, before we continue on, are you going to be okay if I write one line below this, or is that too low? Is it okay? Okay, if not, I can restructure this. You're okay? Okay. But now, guys, we got to go back and we got to talk to our delta H. Delta H is equal to negative 283.0 kilojoules. That's the point. When we flip over the reaction, we change the sign.
So you're going to have to put a lot of energy.
Yes. So now, guys, well, but not maybe the way you're thinking. So now, guys, this is gone. We have restructured this into the thing in red. Now what we do is this. We add everything up. So guys, watch. In the top reaction on the reactant side, we have carbon and we have O2. Do you see what I'm doing? Carbon and O2, bring them down. Then in the second reaction, on the reactant side, we have CO2. So we have carbon, oxygen, and CO2, and then we have our yields arrows. Now on the product side, in the top reaction we have CO2, and then in the bottom reaction we have CO and 1/2 O2.
Oh, I have an idea.
That's the right idea. So now, guys, this. We have a carbon on the left, we have no carbon on the right. Then we have O2 on the left, and we have 1/2 an O2 on the right. So we are going to subtract 1/2 an O2 from each side. Here it goes away. Here we are left with 1/2 of an O2.
It's like very
Yeah. And then, guys, we've got a CO2 on the left and we've got a CO2 on the right, and they both subtract away. And now, guys, look at what we're left. Carbon, a 1/2 an O2, and a carbon monoxide. And now, guys, Hess's law says this. If these add up to this, then the energies of the steps will add up to this. And so now, guys, we do the math, and negative 393.5 plus 283 gives us, sorry, I'm out of room, negative 110.5 kilojoules. And that is the energy that is released when 1 mole of carbon reacts with 1/2 a mole of oxygen to form 1 mole of carbon monoxide. Well, so be careful. That's a double negative. It's releasing energy. The way that we know is because the sign is negative. So guys, that is the process of manipulation. What do you think? I don't know what that means. What do you mean variables?
With like algebra.
I'm just looking at it like I saw it algebraically. I saw the line is like equal sides. Things are on both sides of the equation.
So it's-
Oh, yeah, yes. That's called Math. Yeah. 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 Go ahead, Piper.
So if I got a question and so it's like the first part, like the
Yeah.
and then instead of like, so if you don't have to like use it, can you just like put rivers in?
Yes. Yeah. Yeah. So, guys, I love what Piper's doing because she's asking herself the big questions about what could this look like down the road. So, yeah, if you've got something that you don't need to manipulate, leave it alone. But understand there will always be at least one you need to manipulate. Guys, this gets really evil on the AP test, because they will actually sometimes give you the black equations, the ones to manipulate, ones you don't even need. It is terrible. Yeah. Guys, one other thing. Are you okay with the thought and the logic and the process? Okay. And Adam, I know you guys are talking about good stuff, but you're going to benefit from being a part of this. Guys, understand this is all bunk, but imagine that this reaction balanced, I don't know, let's say a 2 right there. It doesn't, but imagine that it did. Guys, what would you do? And the answer would be, this is where our carbon monoxide is. And so not only would we have to flip it, we would also have to multiply everything by 2. And when you do that, all you've got to do is also multiply that by 2. So if the location doesn't match, flip the equation over and then change the sign. If the numbers don't match, multiply the one that doesn't match to make it match, but you have to multiply all of them and then also multiply the energy change value. Yeah.
So, would it be okay if we were, like, for instance, in this situation, if we looked at it, realized that the carbon monoxide needed to be manipulated, and just switch the sign if we just did that?
Yeah. So I think I understand what you're saying, but yeah. So Dallin, if I understand correctly, this was C plus 1/2 O2 yields CO. And I think if I understand what you're saying, you're like, wait a minute, if the CO's over here and the CO is right there, can I just flip the arrow, change the sign, and go on my way? And the answer is yes, but be careful. Because my experience has been, you understand that you flip the arrow over, but really what you're doing is flipping the equation over. So what that means then is that these are a reactant, and that is now a reactant. Because they do want to see you, and guys, you got to hear this. You have to demonstrate that these do in fact add up. And so this is not just extra happiness. They have got to see your process where you're crossing things out. And so the problem is, what I've found is if you just flip the arrow, you're probably going to forget that this is now a reactant. You know what I'm saying? It's a great question though. You guys good? Please.
So, after we flip the equation, we get CO2 on the other side, and we flip the energy, and then we put the two equations into the same equation.
Yep.
Why can't we just drop the yields arrow? You probably already played this. So it becomes, I guess I'm confused about the step in between having the two equations flipped with all the reactants and products to the right side of each other, and then making that into one equation.
Let me try. So when we bring these down, I wonder if I can get rid of what I wrote in green. I can't, so it's a mess. So when we bring these down, these are the reactants from the first equation. This is the reactant for the second equation. Those come down. Yeah? Okay. Yep. No, you're good. Are you sure? Okay, go ahead on me just a second.
So after
Yeah.
What allows us to cross out the one
Yeah. And I know this,
alone?
yeah.
Like what allows us?
Yeah, so this is that idea that you were saying about variables or whatever. Think about it this way. Let's do carbon dioxide. If carbon dioxide goes in, and if carbon dioxide let me do this a little differently. Guys, please hear this. This is interesting. So what's the point of all of this? We're tracking energy, right? So think about it this way. If energy has to go in to break down carbon dioxide, and if energy then comes out to make carbon dioxide, mathematically that's a wash, because the same amount of energy that goes in to break it came out to make it, and as a result those things would cancel out mathematically, and so we don't include it in the energy term because in and out is the same. We did. So we crossed it out on both. We crossed it out here. Yeah, so let's do that. So, I mean, it's a weird fraction, right? But what we started with was half a mole of oxygen right here being formed. And we had a whole, getting rid of the half because it came later. So we had a whole mole of oxygen breaking apart. Say that that's 100 joules. But we only made half a mole of oxygen, so we only got 50 joules out. So if 100 joules went in to break this, but only 50 came out because we only made half a mole, then all we have to do is we can forget about this and only worry about the difference, which was the 50 that still went in. That's why we get to cancel them. I've never had this conversation before, and I've done this a long time. It's cool you guys are picking up on this. You guys good? Okay. So guys, now the thing that was really fun for me to figure out a couple of years ago. You are now going to learn to do these not through manipulation, but through computation. In order to do that, you need to understand, I'm drawing dots. You need to understand one new idea. So guys, these are what are called, wow. Oh, are you sure you want to quit? No, I don't want to log out. Oh, that's what I want. So guys, these are called enthalpies of formation. Write it down in your notes. So an enthalpy of formation is the amount of energy needed to make 1 mole of a compound from its component elements. Oh my gosh, I said that exactly and I didn't even read it. Whew. So guys, think through that. It's the amount of energy needed to form 1 mole of a compound from its component elements. A couple more thoughts and then we'll dig into it. It is abbreviated delta H naught sub F. This is the abbreviation for enthalpies of formation. And by the way, guys, you're going to see in this class, you're going to see in college, we just call these heats of formation. They're technically enthalpies of formation, but you'll see if you write heat of formation on the AP test, you're fine. This one gets really loose. But guys, let's talk about this delta H naught sub F. You guys all know delta means, H means enthalpy. The F subscripted means formation. Guys, what about the circle? It's not degrees, it's read knot, K-N-O-T. Do you know what it means? Standard conditions. So guys, that means at standard conditions. You can ignore it because everything we do is at standard conditions. 0 degrees Celsius and 1 atmosphere of pressure. Don't worry about it. All right. So just one second. Oh wait, I already did that. Go ahead.
So if it's at standard conditions, do you necessarily provide the
You do. You've got to write the not, but just ignore it. We'll always be at standard conditions.
This is the formality.
Yep. So again, and guys, oh wait, I was wrong. In these in gases, standard condition is 0 Celsius. For these, it's don't worry about it. You don't need to know. But guys, do this. Grab your books and open up to page 185. Another table. Yes, you have to memorize the whole thing, or it'll be given to you on the test. There you go. Hey, so guys, take a moment and allow your eye to scan over this table if you would. Obviously, this is not exhaustive. There's a heat of formation. Notice I said heat. There's a heat of formation for every compound on the everywhere. This is a few. But guys, I'm interested in what catches your eye.
It's a lot of energy to make sucrose.
Oh yeah, right? Which is why it's such a great source of energy. Guys, what else catches your eye? Yeah? Go ahead. Say it again. Oh shoot. Y'all, we need to talk. JD pointed out, is it really 5? You counted them? Love it. So guys, they're in this table, not exhaustive, but in this table, there's 5 of them that are positive. Most of them are negative. But guys, if you understand what you're looking at, none of them should be positive. So let's talk about what you're looking at. Guys, let's do water. Let's do sodium chloride. So guys, what does this number represent? And the answer is this. Looking at sodium chloride, our product is sodium chloride. The delta H is negative 411.1, and that's kilojoules per mole. But guys, if you understand what heat of formation is, this is the amount of energy needed to form 1 mole of a compound from what? Sodium and chloride. So guys, let's talk. When sodium, well, let's do this. When sodium and chloride come together, they bond together and energy is given off. Yeah? Forming bonds releases energy. Now, guys, what has to happen to these reactants? Well, they have to break apart, right? Kind of like we said with methane and oxygen. These have to break apart, and that's endothermic. But guys, these are elements. How much energy has to go into breaking down the elements? None. They're already elements.
Except for the diatomic.
Well, but then that's the thing that's interesting, and that's what Nathaniel got to earlier. We'll talk about that in a minute. But guys, if you don't understand what we're saying, remember when we burned methane and we said you've got a carbon and 4 hydrogens, and so energy has to go in to break these into their elements? They're already elements. So guys, the delta H's should all be negative. Yes? But as JD pointed out, some of them are positive. What the snap is going on? And it has nothing to do with the diatomics. It has everything to do with chapter 19, and we're not going to talk about it yet. I know. Guys, it actually is not an enthalpy issue at all. It's an entropy issue, and we're going to talk about that in a couple days. But guys, for right now, you should understand this. These heats of formation should all be negative numbers, because you're taking elements and you're making compounds. So then, guys, and I hope this is in the notes, what about, guys, what about the diatomics? This may freak out. Yep. Guys, you ready for this one? The heats of formation for the diatomics are all 0. So guys, the heats of formation for all of the diatomics is 0. Write it down and then we'll talk about it. Just so you know, guys, I think we might bleed 2 or 3 minutes into break. We'll still take a break, but we might need an extra minute. Nathaniel, I see you. Let's let people get caught up and then we'll talk about this. So guys, what's going on here? So let's set the stage. Don't write any of this down, but let's set the stage. So we just talked about the idea that sodium and chlorine makes sodium chloride, and we understand that that value is negative because there are no bonds being broken. There are bonds being formed, and that gives off energy, right? So what about the diatomics? So what about O2? Doesn't oxygen have to react with oxygen? And when it does, doesn't it then form a double bond? And shouldn't that energy be represented as released? And guys, the answer is no. Why is the answer no? Let me do this. You won't get it. Sorry, Dylan, that was harsh, but you won't get it. So guys, the idea is this. Is energy released when one oxygen bonds to another oxygen? Yes. Energy, we're not breaking the rules. When things bond together, energy is released. So when oxygen binds to oxygen, there is energy released. But guys, we are saying the delta H for this is 0. The question doesn't negate chemistry. So guys, when oxygen bonds to oxygen, energy is released. So why do we say that it's 0? And the answer comes back to our definition. From its component elements. And guys, the elemental form of oxygen is O2. That's the difference. Because you don't find oxygen on its own, we don't consider, if you will, the origin of oxygen to be elemental, and then we say, oh, some energy was involved in diatomic. Because our starting point is the elemental form, and because oxygen's elemental form is O2, we call that our baseline starting point, and therefore we say energy is not released forming O2 because that's in its elemental form. Do you buy it? Go ahead.
So we're doing a reaction,
Oh, we're gonna.
and we have oxygen.
Yep.
And none of the oxygen is reacting in its diatomic elemental form. It's all in compound.
Yeah.
And then on the product side of the reaction,
Yeah.
there are diatomic oxygen.
Yeah.
Is the formation of that diatomic still 0?
Still 0. Yep. Because it just became its elemental form, and by definition, yeah. Go ahead.
Alright, so I've got a couple questions. This one's
Are they hard?
I'm having trouble with this. First one is I've learned about nitrogen.
Yeah.
How it's triple bonded.
Yeah.
So it's really hard to break apart.
It's the hardest thing to break. The strongest bond that we know of is the triple bond in nitrogen.
So how can that take so much energy if the energy isn't, if there's no energy released when it's stitched together?
Yeah.
How can it take so much energy to break apart?
Yeah. Yeah, but in this calculation, we don't account for it. Yeah, right? So, exactly. It's less of a question of what's really going on and more of a question of accounting. And when we do the accounting, we assume that the elemental form is N2.
The other half of that is sodium chloride.
Yeah.
When they bond form sodium chloride,
Yeah.
Energy is released from that bond.
Yeah.
Where did that energy come from?
Yeah.
You say that on the left side.
That's a brilliant question. So, where does energy come from? That's a big question and lots of really interesting YouTube videos. But seriously, it's the case. I'm going to ask though, but I know that you're asking the question desiring an answer. we're going to take a pass on that. So that fundamental question, where does the energy come from? Part of the answer to that we're going to find in chapter 19. Part of the answer to that question is going to come in 2 units, because we're going to talk about bond formation. And when we do, you have this idea that when sodium and chlorine bond, sodium gives up an electron, chlorine gains it, positives and negatives attract, and that's salt. That's not true. That's what you learned last year. When we talk about what's really going on, you're going to better understand the answer. Yeah, so some of it is we damaged you last year in Gen Chem, and we have to fix it. We just can't do it now. So, guys, we're going to move forward. So do this with me then. Guys, we are now going to do another figure out the energy of the reaction. Now, guys, this is the reaction that we're going to study. I'm going to encourage you to not write this down. Because, guys, when you write this down, I think that let me say it differently. If you're writing this down, you're going to miss the magic. And guys, the reason that I'm comfortable with you not writing this down is because actually what we're going to do is we're going to solve this one using manipulation. I know you're like, wait, I thought we got past manipulation and now we're back to it? And the answer is yes. We're going to solve this using manipulation. So guys, do this with me. So we've got HCl on the left. Down here it's on the right. So what do we have to do? We got to rearrange it. So guys, we've got to flip this over. Dallin, I'm going to do your trick. Guys, we've got to flip this over, so we're going to do this. But then, guys, what else do we have to do to make this work? Yeah, we've got 2 HCl's there, and we've only got one there, so we need to go, oh, guys, tell me. Is that too much of a mess? I don't like it. I'm going to rewrite it. It just doesn't sit right with me. So guys, I'm gonna clean this up and redo it. So this one then would become 2 HCl's yields H2 plus Cl2. Is that okay? Okay. Now guys, let's do our next. So we've got calcium hydroxide. Do we need to do anything to this?
Yes.
What do we have to do? Flip it. Do we have to multiply? No, so we need to flip it. So guys, when we flip this over, we will get CaOH2, and our products will be calcium, oxygen, and hydrogen. Now guys, moving along, we've got CaCl2. We find it here. Is it in the right place? Is there the right amount? We're good. Now guys, we've got water. Is it in the right place? Yes. Is it the right amount? So let me see if this is better. If I go 2, and then 2, and then can I just make this a 1? Is that okay? Okay. So guys, do you better now understand the manipulation process? You okay? Okay, now do this. Grab your books.
Oh yeah, because it didn't give us the...
It hasn't given us the delta H's. So guys, we're going to use the table on 185 to get the delta H's. So the first one that we need is the heat of formation for HCl. So guys, some of you right now are asking yourself, wait a minute. Why are all of these values in this table? Guys, what is this table? Heats of formation. But guys, look. What kind of reactions are all 4 of these reactions? If you just saw this on a test and we said this, I think I can do this and not get in trouble. Guys, if you just saw all of these reactions, what kind of reactions are those? Synthesis reactions. Aren't all formation reactions synthesis reactions? Yes. So guys, we can find the delta H's for these reactions By looking at the heats of formation, because this is the formation of all of these. Yeah. Maybe.
I mean, that's what we're about to do. We have
Maybe.
those days to.
So guys, do this with me. So HCl, what is, and I'm going to just put, if I may, I'd love to switch colors. I didn't. So guys, this is cool. Stick with me. All right. So guys, moving back here, zooming in, I think this will be the best way to do it. All right. So now guys, what we're going to do is we're going to come up with our delta H's. Okay. So we've got HCl. Let's just use round numbers, 92. So now guys, the delta H for the original reaction is negative 92. But what do we need to do to make this usable now? So we flipped the reaction. So that means we needed to change the sign. And then also we need to double it. Good? Now guys, this. What about for the calcium hydroxide? Calcium hydroxide, sorry, that's loud. Did they take it out? Shh, Nikes. Those little trickers. What page are we on? Thank you. Oh yeah. Yeah.
No, for every element ever in the universe.
It's true. I feel like there are more numbers than there are pieces of paper.
Guys, we're going to just continue on. By the way, there's a bigger table of these in the back of the book. You don't need to go there right now.
As we all immediately start cooking.
I know.
Yeah, but where?
So guys, the number is negative 990. Don't spend time going there. Stick with me. So guys, the number back here is negative 990. Now, do we need to make any adjustments to this?
Yes.
What?
990.
Change the sign? You okay? So guys, let's summarize. What have we done? So what we did is we had to change the sign for both of these numbers because we had to flip the reactions. Then guys, we had to multiply this top one by 2 because it balanced, because there were 2. Now guys, this is calcium chloride there. Oh, do you have the number in the back?
Yeah.
What, please?
It is negative 795.
Thank you. So guys, this next one is negative 795. Now, do we need to do anything with that number? We do not. And then guys, the last one we need is water. Let's use liquid water in this case. And guys, that number is negative 285. I'm being loose with numbers. Now guys, don't look away. This is good.
Very integrity.
Yeah, don't look away. Do we need to do anything with this number? Double it. Do we flip it? No, just double it. Okay. So now guys, follow these questions. You're about to have a moment. So notice that the first and the last, well, reactant and product, we had to double. We had to double them to make, and guys, we could go through and add these all up and we would find that it adds up. But guys, the first and the last, just, you really want to see this. We had to double. But guys, at the end of the day, the reason that we had to double them was because of these twos, the stoichiometric ratios. Now guys, this. The other change we had to make is we had to change the sign of the first two. Guys, listen to the logic. So we understand that all four of those reactions are heats of formation. But guys, listen. Reactants are not formed. Reactants are consumed. Yes? So guys, because reactants are consumed and not formed, we don't need the reaction that represents the formation of the reactants. We need the reactions that represent the decomposition of the reactants. So we have to flip those over. So guys, let's now summarize what we just said. To make these numbers useful, we had to flip over the reactants because they are consumed and not created. The other thing that we had to do was multiply by the coefficients from the balanced equation. Guys, does all of that make sense? Okay, here's the deal, guys. If all of that makes sense, then this makes sense. No, write it down. Guys, this is the difference between a good high school chem teacher and a college professor. A college professor would throw this on the board and say, get it. A good high school teacher spends the time to help you understand the logic. But guys, and not with the noises. Guys, if you understand, and you all signed off on it, I get it. We flip the signs for the reactants because they are consumed and not created. And we multiply by the exponents because we could be making or consuming more than 1 mole of a reactant or product. But guys, if you understand those ideas, you need to understand that math, those ideas are represented in the math. So guys, let's talk when you're caught up. I'm going to roll on this one down. You guys ready? Not yet. So guys, let's pick this apart and let's figure this out. You ready? So, what do we know? In order for the math to work out, we need heats of formation. That's what we got out of our book. Then guys, what did we do? Why did we flip the reactants over? Consumed, yes? Why did we flip the reactants over? They're being consumed. But when we flip the reactions over, we change the sign. Then, the other thing we had to do is account for the fact that it's not 1 mole the whole way through. So guys, where is this represented in this equation? Well guys, this represents multiplying by the number of moles. Like the first and the last that we had to multiply by 2. Guys, N represents the number of moles. So when you set up this equation, you plug in the coefficients from the balanced equation to account for the fact that it doesn't balance with all ones. Now guys, the other thing that we learned is this. We changed the sign for the reactants because reactants are consumed and not created. Guys, where is that represented in this? The subtraction. If your math chops are good enough, guys, maybe you understand that what this actually means is add them up, but make this negative. So guys, that subtraction sign functionally changes the sign of all of the reactants so that they become the opposite because they're becoming consumed and not created. Good? Now this. Once we finally got to the end of all of this, and we didn't do it, but when we got to the end of all of this, guys, eventually what were we going to do with all these numbers? Add them up. That's Hess's law, right? We were going to add them all up. So guys, where in Earth am I? Never a loss for an unproductive comment. So, guys, where in this equation is add them all up? That's the sigmas. Guys, sigma means to add up. And then finally, what values are we adding up? The heats of formation for the reactants and the products. Guys, you don't understand what you just experienced. Because in college, they expect you to understand this stuff at that level just by throwing an equation in front of you and saying, figure it out. Instead of that, we got down to the nuts and bolts. And guys, this was the neat aha moment that I had when I taught this like 4 years ago. I used to just teach manipulation and computation separately. And then I started picking at one of these in front of kids and I'm like, wait a second. That equation is just manipulation in equation form. It's exactly the same stuff. The negative says flip them over. The ends say multiply by how many there are. And that's all you're doing when you do manipulation. So guys, this equation is literally the equation for manipulation. I thought that was kind of cool. So, guys, with that said, we're going to spend a minute. We're going to solve one of these. And off we go. And then we will take a break. Guys, grab your AP equation sheets. Guys, I know we're pushing long. Thank you for being willing to engage. So guys, grab your AP equation sheets. I think it's the page 4. Yeah, page 4. You see it? Find the equation that's up on the board. See it there? Yeah, what's missing? The ends. Guys, for some reason in the AP equation sheet, they do not include the ends, but they're to be there. When you write down the equation, and guys, we'll talk in a minute. When you write down the equation when you're taking a test, you do not need to include the ends because they're not on the AP equation sheet, but they expect you to know to use them. Okay. So guys, join me then at this. Don't write down the question. It's on our notes. It's actually out of the book. But the question is, calculate delta H, the enthalpy change, for the combustion of 1 mole of benzene, C6H6, to produce carbon dioxide and water. So guys, here's the trick. We've got to balance this thing. But when we balance it, there has to be a 1 right there. So if there's a 1 right there, we need a 6 right there, right? So now we have 6 carbons. But then guys, we also need 6 hydrogens, and that gives us a 3. Watch this. Oh yeah. So guys, how many oxygens do you have on the right side? 15. So this equation then balances with 15 halves. All right. Now guys, this is how to solve this problem. This is what they are expecting on the AP test. So what you do is you start with the equation. I want to write it down exactly as it is on the AP sheet. So guys, you have, and you know this, you always start with the equation. So we've got the delta H naught, and they don't say reaction, okay, is equal to, I'm going to center that a little better. No, it's okay. Actually, I shouldn't. I should move it further to the left. Okay. So delta H naught is equal to the sum of the heats of formation of the products minus the, whoa, that was exciting, minus the sum of the heats of formation for the reactants. Now guys, this, you ready? You're going to get really strategic with parentheses. So the first thing we need are the heats of formation for the products. So what are those? Well guys, it goes like this. It is the sum, so we're going to do that in parentheses, of 6 times the heat of formation of carbon dioxide. Plus 3 times the heat of formation of water. Close parentheses minus the sum of 1, and you don't need to put it, but I will, the heat of formation of cyclohexane plus 15 halves the heat of formation of oxygen. Not yet. You still have to write it down. And guys, I should just warn you on this. On the AP test, there's no partial credit, right? So when you have this question on the AP test, what they'll do is they'll check your answer. If it's wrong, they just stop looking. But if it's right, if you didn't write down the equation, and if you didn't do this setup, you lose the point, even if you did the math right. So now guys, we continue and we plug in numbers. So we have 6 times the heat of formation of carbon dioxide, which is negative, right out of the book, 393.5 kilojoules, plus 3 times the heat of formation, I think, is it liquid water? Does it even say? Liquid water, negative 285.8 kilojoules, minus 1 times the heat of formation of benzene, which is 49 kilojoules, maybe 49.0, yeah, we're okay, plus 15 halves times 0. That made things a little easier. And now guys, we dig in. So we have 6 times negative 393.5 plus 3 times negative 285 So guys, check me. I get negative 903.4. No? Okay, let me try again. So,
I got negative 3267.
all right, so 6 times 393 is about 2400. Oh yeah. Sorry, negative 3267. Yeah. So negative 3267.4 kilojoules. And that is the heat. No, that is the heat of this reaction. It's not a heat of formation. It's the heat of reaction when 1 mole of benzene burns in the presence of oxygen. It's a lot of energy. Yeah.
So I'm still confused on how if we're trying to calculate the heat, so the energy that's produced in the reaction, how we can get away with just ignoring the energy that it takes to bring the oxygen up.
Yeah, no, and I appreciate your unsettledness with this. So I understand what you're saying. So when oxygen, in this case, breaks down, realistically, there has to be energy going in, right? And we talked about the idea of it's because of where we determine our starting point to be, right? Which still isn't satisfying. And Adam, I'd love to do this conversation with you individually. In order to really have the conversation about how this works, we would have to talk about state functions. And if you remember, we said we're not going to, and I want to protect that. I still stand by the idea that we can do this and actually understand it at a pretty good level and not have to talk about that one little sticky spot. If you'd like to individually, I'd be happy to, but we'll have to go back and talk about state functions. Okay, go ahead, Dylan.
So I know where you got the 15 from and the 15 over 2.
Yeah.
Did we get the denominator from just the original amount of 2?
No, we got the denominator from the fact that it comes in packages of 2.
Yeah.
Yeah. Oh, yes. Then yes. What I meant to say was yes.
Okay, so if it were like 03,
Yeah.
it would just
Be 15 thirds. Yeah. Yes. All right. So, guys, wow. Homework. This is it.